Hello YouTube, today we're going to talk about the atomistic, which is the study at an atomic scale of the atoms, logic. So what's an atom? It's a core made with neutrons and protons, and maybe other things we don't know yet. And around it there is a giant cloud of electrons. So you don't know where the electrons are, but they are there. In terms of space, the electrons, the atom is 99.999% empty, so it's not very heavy, obviously. Okay, so let's talk about it. Let's get in depth with that. Okay, so what we have, what do we have, what do we have? At first, we can study the, wait, we can study atoms as being, fuck, okay, stupid scale, as being a point. You can use it mainly in physics to do bouncing with the Brownian movement, but we'll have a more chemical approach. So obviously we'll not consider it's a point, but you can actually study this. It's interesting. Okay, so an atom has a core, and usually you never touch the core. Wait. I don't know if it's called a core or not. So you have something that is very huge, and around it there are little electrons. Well, I'm going to draw them bigger. Okay. The first thing we noticed is that you could actually draw circles. And unite the clouds of electrons in different layers, and that you'll find the same number of electrons per layer, per form, every time. So it meant that an atom does not share electrons spontaneously. If it doesn't chemically react, nor physically reacts, nor nuclear reacts, it means it doesn't do anything. So it means that electrons stay here. And in fact, the electrons get the same, stay on the same clouds, the same layer of clouds, if they don't react. So we will give each of these a mathematical expression. Okay, so to define an electron, we'll have a notation LMNL, four numbers. Okay, what's n? N is the number of orbital. So it means, if I'm saying shit, let me check. Yes, it's the orbital. So it means that it's the layer. It's one of the layer of order n. So it's just a number, orbital. L, and this is an integer. It's an integer. Then you have L. L, it's the thing, you know, no, just I forgot, I haven't done this in a while. N is the number of the layer, and L is the letter of the layer, is the letter of the layer. Yeah, it's another number, but usually use it as a letter, and it goes from 0 to n, well, to n minus 1. 0, 1, etc., etc., until n minus 1. N minus 1. Okay. Then, more interesting. This is a revolution. No, this is a quantification ML that gives us the possibilities. So it goes from minus 1, minus, wait, minus L to L, and it's an integer. Honestly, I never used that, and this is why I forget about it. It's kind of boring, to be honest. Okay, and now, more interestingly, the ms, number of spin, it's either minus 1/2 or 1/2. Okay, now let's, fuck, I'm stupid, it wasn't showing. Okay, it's either minus 1/2 or 1/2. It means that on the cloud, the electrons will spin either in a direction or in another direction, only in one sense, because it's spinning around. Well, it's going around the atom, but spinning at a speed minus 1/2 or 1/2. So it depends on the sense of rotation. Yes. Okay, so now interesting stuff, because obviously this is just bullshit, tbh. Okay, so each, where is it? Okay, new drawing. Okay, so then you will try to okay, so each of the layers have an energy associated with the layers. So you'll draw, shit, I'm not red, I'm black. Okay, this is not an axis, and this is an axis, and this is energy axis. At first, there is the n equal 1, so the orbital 1. You just place it here. It's the main. You always have it in every atom. You call it 1s by definition. 1s. It's 1s. There it is. In it, you can put 1s. You can put 2 electrons. And there are actually laws that define how to put these electrons. So there is the rule of the principle of Pauli. The principle of Pauli states that each of the quantic states defined by the 4 numbers is occupied by 0 or 1. 0 or 1. Which means that in an orbital, so the thing I just drawn, there is either each case, because in 1s2 there is actually one quantic case, there is either no electrons, 1 electrons, or two electrons. but the spins must be reversed, because else the sum of the spin cannot be zeros or 1. Because if you sum it in reverse senses, then it cancels out. Okay. Yes. So that's how it works. Every case has either 0, 1, or 2, but 2 in reverse senses. The rule of Kleshkovsky, when you fill out when you fill the atomic orbitals, you have to first follow with n plus L growing, and then you have to fill the orbital with n lower first. So it's kind of complex, but you can actually put electrons. So I'm going back to my thingy. Where is it? Where is it? You have, okay, this. So as we stated earlier, there are 1 and 2 electrons if it's not an hydrogen. So this is a quantic case. So with this quantic case, you can have, as I said, 0, 1, or 2, and 2 in reverse senses. Then, with a higher level of electrons, of energy, you'll have another, which will be some number n, and some, okay, I'm going to write it, raise number that comes from n, and a letter that comes from L, the two quantum quantum informations. And then, depending on how many cases there are, you'll have some of them, and you'll have to fill them. But some layers will happen to be at the same energy level. So then you'll have to use the rule of Pauli, the rule of Kleshkovsky, that says that it's by growing growing n plus L, and then with equality we must fill out the orbital with n, the weaker, first. There are exceptions to this. I'm not going to talk about them. The rule of Hund said that if a level of energy is degenerated, so it means that if there are not enough electrons to fill out, so for example, if there is a case with only 1, we call it degenerated. Yes, what am I saying? Yes. Okay, it's degenerated, yes. If there is only 1 sense, 1 electron, it means that it's alone. So the atoms is paramagnetic. So the rule of Hund will tell that if there is this in the structure, this will be the highest level of energy in the whole atom. So it means that all other have to be followed, which means that if you have this, then there is no quantum cases with higher energy level. So this is known as the Pauli-Kleshkovsky-Hund. These are the main rules to study it. So Pauli, each of the quantic states are occupied either by zeros and 1, which means it's either 0 electrons, 1 electron in one sense, or 2 electrons in two senses. Kleshkovsky says that you have to fill out the orbitals either by n plus L, by growing n plus L, and if you can't, you have to fill out with growing with the lower n first. The rule of Hund states that when level of energy degenerated, meaning that the electron is alone in its quantum case, it is the state the most stable with the maximum of electron non paired. So 2 upwards is more stable than this. Okay, so let's do an exercise. We okay this okay. Oh shit, I can't do that. Forgot. Okay, like this. For example, I'm taking the okay an easy one, please, an easy one. I'm taking okay, I'm taking the argon, which is a noble gas. So if you studied a bit the periodic tables, you know that each of the noble gas have stable structures. So you will write that it's exactly the same structure at as the previous noble gas, higher in the thingy, in the, how do you say it, in the classification periodic of Mendeleev. Sorry, but there are obviously new atoms, new electrons that you need to put in your orbital. So since Ne is actually, I'm going to, usually you just put the noble gas and you don't develop it, but it's 1s2, so it means that the orbital 1s, so n equal 1 and s is the letter of L equal 1, you can put 2 electrons. So you have 2 electrons filled already, and argon has 18 electrons to fill. Okay, okay. You have to fill out everything. Okay. Now the second one is 2s2. Why? Because you have growing n plus L, and you have to grow something, so n grows. Then you have to have the growing p, the growing L, so the L will go to 1, but the letter associated with L equal 1 is P, and P can actually handle 6 electrons. Magic, because I can't explain it very easily, but with the quantum case, you have just 3 more in this orbital. Okay, then where is it? Then you have the growing n, so the number 3. Then s, because you come back with n plus L growing. So oh yeah, I can do it like this. So now with the other principle, the principle of, how is it called? Principle of Kleshkovsky, you have this. So you have to place the layer 3s, and you have to place the layer 3p6. Yeah, 3p6. Okay, so you have this by n plus L growing, but you say that if n plus L is growing, you have to put the first more. So this is n plus L equals, this is 3, this is 0, so this is 3, and this is 4. So you have to place this one first. But then you have this one, and the following, well, you can't place it for argon, so I'm going to swap with uh, titanium, which no, not titanium, something bigger. I'm going to swap to krypton. 36 electrons. It has the structure of argon. Then you have to, so the last one was n plus L equals 4. So you have to put the n plus L equals 4. So you have 4s2. But then you have the choice between 3d10 and 4p6. Okay, so n plus L, 3, n, and d is the letter associated with L equals 2. So 3 plus 2 equals 5. And 4 the n, and p is associated with the L equal 1. So 4 plus 1 equals 5. So both have the same n plus L. And if you don't have the Kleshkovsky rule, then you are pretty much screwed because you can't sort out the layers. So what will happen is that you'll first fill out the n plus L drawing, but there is the equality here. But then you'll do the one with the list of n. So the 3, you'll put it first. Okay, so I guess it's all for the general cases. You can do non-quantic stuff with that and study lots of energy stuff. It's very interesting. The quadruplets NL, ML, and MS is a quantic state. I don't know if I said it. Okay, so now about exception. I'm going to talk it really quickly. What happens is that sometimes you don't have enough electrons to fill everything. So one of the electrons will prefer to give it so that it doesn't verify the Hund-Kleshkovsky-Pauli rules to do some things. And this is very, very complicated, but it can happen that the rules aren't verified. And I let with you with that, and I hope you liked this thing about atomistic, atoms, electrons, and boring stuff like that. Bye.